I thought that let me take a break and just tell you a little bit about one of the methodologies which is being looked at as a way of facilitating innovation. So this is the person, Genrikh Altshuller, who came up with this method, known as theory of inventive problem solving. He used to work in the Russian Navy. He was a patent officer there. This person felt that innovation is something that can be learned, you know, and he came up with a structured methodology. That's what I will tell you about today. He apparently studied very large number of patents. It goes anywhere between 50,000 and 200,000, depending on whom you are referring to. And interestingly, many of these patents that he read and this whole theory that he developed, it was while he was in jail. He was actually put in jail by Stalin. Only after Stalin was no more that he was released from prison. Very, very intelligent person. What he did was, of course, we all read patents. Like he read the patents and this large number, and what he was trying to do was that he was trying to find out are there some recurring themes in how they are trying to solve whatever problem it is that they're trying to solve in the patent, and that's what he was trying to find out. And he said, yes, we find that it's always falling into some kind of themes. So he picked out those themes. What are these themes? And then he said, if people can be trained to pick out such themes and then be able to solve those or find out how one might be able to get a suitable solution, then that would be wonderful. So that's what it is. Now, I have read this, didn't understand all of it, but I didn't find all of the things that he said to be so useful. And I understand that he himself abandoned parts of his approach in later years. But then what I did find is certain things that he said are extremely valuable and will always remain valuable. Doesn't matter whether it is today or tomorrow. So those are the things that I will perhaps discuss a bit more with you as I go along today. So this is his most important principle. One is, as I said, why was he looking at the patents? He said, whatever you try to do, you'll find that someone somewhere has already solved your problem or one similar to it. And what he said is, creativity means finding that solution and adapting it to the current problem. Obviously, you cannot use that solution exactly in toto, because that may be a different problem. But there's a huge amount that one can learn. So that's what he means by a problem similar to that. Then he said that, if you can learn and just adapt it to your particular situation, that might be the fastest way to solve the problem rather than thinking all the way from scratch. It may not be necessary. And this is something that I would encourage all of you to do, that there is a lot out there. You just have to be smart enough to pick it up. And then what he said is that most of these things he found have something to do with contradictions. And what he said is, don't accept contradictions, resolve them. Let me tell you that over the years, when I was looking at contradictions in our own work, and some of those things actually spurred invention. Our institute was quite big in the area of reverse osmosis. As I'm doing reverse osmosis, I obviously want to reject as much of the salts as possible so that the water that I get is as pure as possible. That's one. The second is, for a given pressure, I want to maximize the output in terms of the flux. Generally, it was believed that if you try to increase the salt rejection efficiency, okay, that it would mean that you will compromise on the productivity of the flux, which you don't want. You really want the best of both. Take another case. I remember this used to be a burning issue around 99, 2000. Of course, most of the salt is produced from seawater, but there were also underground brines in many areas from which you could produce salt with very high productivity because those brines were actually much more concentrated than seawater, maybe something like 3 to 4 times as concentrated in some cases. So obviously, people wanted to use those to produce salt because in less area I can make more salt. But the problem was that it will give you higher productivity of salt, but the salt will be of a poorer quality. The belief was that because the composition of those brines is different from that of seawater, and that is the reason. Okay. Or if someone says, I wanted extremely pure salt, and there is no other way to do it than, let's say, by recrystallization. You can say, let us just use solar energy, dissolve the salt again in seawater, and then allow it to evaporate out in the open pan. And honestly, you can get extremely pure salt through that kind of recrystallization, but it increases the land requirement. So you may require about 10 to 15% more land. And so that was again a major issue. Where will this land come from? So obviously, how do I resolve this contradiction that I can still make use of solar energy, do recrystallization out in the open in the fields, but at the same time not increase the land area? Or let's say there is a membrane, the ultrafiltration membranes, which are excellent for rejecting pathogens. So if your water is contaminated, let's say with coliform, so you might be able to pass it through these ultrafiltration membranes, and you might be able to make germ-free water. Now, actually, the people who require it the most are, let's say, people in villages, because many times they just pick up water from the ponds. Those water is they've got a lot of pathogens in them. But the problem is that these ultrafiltration units, they require adequate head, because you need some pressure to push the water out of the membranes, because the spores are very small. Now, the problem is that you can, of course, do it with a pump, but these very poor marginal villagers, many times they don't have electricity in their house. They may not or we may not be able to afford a pump. Okay, and they all live in just their huts. There's no head, so they can't generate that pressure. So how do you solve this kind of a dilemma that the people for whom you require this water the most, they are the ones who are least in a position to carry out this kind of a process. So again, a contradiction. This is what innovation is about in many cases. It's about resolving contradictions. People say, yeah, but what will we do? Subsoil brine and seawater are different composition. But then that does not help us at all. It is like being fatalistic about it. But if you say, who said so? The composition is not the only thing. There's so many other things to look at, and maybe you can resolve a contradiction that way, or you could find a particular domain in which the contradictions are minimal. That's, for example, what we did when we were able to make a better reverse osmosis membrane, where you could get a good flux as well as you could get a good salt rejection efficiency. And it was all about finding that particular area where really the this kind of contradiction was minimal. So that's what he means by resolve them. So what he said is that in his view, you can define the majority of problems in terms of certain features. And he was able to broadly define 39 features, now, also you have to remember that he was a mechanical engineer, So maybe he came at it a bit more from the mechanical engineering end. But I thought, looking at some of this, I said maybe it is not that it cannot be applied to chemical technology. Maybe it can. It's probably much more general than you imagine. Okay, because when he was reading those 40,000 patents, or later on even more, it's not as if he was only reading mechanical engineering patents. He was reading all kinds of patents. So I don't think he was so narrow in his perspective. Okay, but you will find there are interesting features: weight of moving object, weight of stationary object, length of moving object, length of stationary object, area of moving object, area of stationary object, volume, speed of object, force, stress, shape, stability, strength, durability, temperature, illumination intensity. It goes on and on. Loss of energy, power, loss of substance, loss of information, loss of time, quantity of substance, measurement accuracy. It's quite interesting, and it ends with productivity. So what is said is that actually these are the different parameters which cause contradictions in general. And what is said is that you will find that if you are trying to improve, let's say, one of these, invariably you will find that something else is getting worse. And that's what he meant by contradiction. And so what he did was something very, very interesting, where he made a matrix and he wrote down these features once horizontally. So 1 to 39 horizontally, okay? And the horizontal one he called as the worsening feature. And the same thing he wrote vertically, 1 to 39, and he said this is the improving feature. So I can find out which is contradicting with what. And then for each of these intersections of the contradiction, you will get a box. And then he did something else with the box, which I will tell you about. So that is what he meant by features. Now, he also said something else. He said, yes, those features and making this kind of a matrix will help me to identify a appropriate box. And what he did was, based on all the examples that he had dug out from the patents, etc., he identified for those points of intersection, what are the most likely principles which will help you to solve the problem. Let me first show you what he actually did. So he put these 39 over here, those 39 features, and horizontally it's a worsening feature. When I put it vertically, okay, this way, these are improving features. So I couldn't, because it otherwise would get too small. So I broke it up. But you can see overall, I've covered the 39. And for those who feel more comfortable looking at it in one go, this is what it is. These are the vertical and horizontal features. Suppose I say that the strength is improving. Okay, so great, strength is an improving feature. But when I improve the strength, let's say the weight of my object is getting worse. So what I will have to look as is the intersection between weight and strength. So you can see in this box there are certain numbers, and like that, for all intersections, he was able to locate and put some numbers. There are a few where there are apparently no solutions in those that he could find. Doesn't mean there are no solutions, but he couldn't find any. And so what are these numbers? These numbers are what he called the principle. Okay, so he said that if you have a contradiction where there is some improving and worsening feature, and you are able to define the improving and worsening feature, then and I get some numbers, and he said that chances are high that you might be able to come up with a faster solution if you focus on those principles. It sounds so interesting, but in reality, when I went to actually apply it, I found that it is not so simple. Maybe you all will find it easier. But let me now show you what are some of the principles. And principles means the solution or the directions of solutions. Okay. Let's say the first one that he put is segmentation. And I'll try and define some of these things for you. Taking out, local quality, asymmetry, merging, universality, nested doll. Now, nested doll is like whenever I get a telescopic effect, like when the aeroplane is landing, the wheels are out, but moment it's in flight, the wheels will retract, right? And you don't see them. And so it's like a nested doll where you put something inside the cavity of another. Just to give you an example, okay? Anti-weight, preliminary anti-action. You can see it's quite interesting. Blessing in disguise, self-service, intermediary copying, porous material. You will be thinking, what is he talking about? And but these are the kinds of principles which actually appear in those in these numbers. So you have to see, like for example, let's say over here it says 28. Okay, so I'll just say 28, 10, 1, and 39. Okay, which is the intersection of volume of moving object and 30, stability of the object. Okay, so that is the intersection 30. Okay, so 28, 10, 1, and 39. So what it says is that go to 28, 10, 1, and 39. Then you just put it down. And he's saying that don't go through all the principles. Try to focus on these. Maybe those will help you to solve your problem. And how did he arrive at those numbers? Based on the patents. He felt that these were the typical types of approaches that people took whenever there was this kind of a contradiction. And that's how he basically came up with these numbers. It's not as if the people who wrote the patents knew anything about TRIZ, but obviously the other way around, that TRIZ knew about how they had approached and solved the problem. Is that clear to everyone? Everybody understood?
Yes, sir.
Yes, sir.
Okay. When I was trying to look at what were therefore some of the very important problems that, let's say, were solved by this methodology, I found a few which have become quite famous. What I was told is that a lot of people use TRIZ and solve their problem, especially in Germany, apparently. But many times these are done by industries, and they don't want to share the information. So a lot of it is actually in the private domain. You can't access it, but apparently Boeing, they shared how TRIZ was used to solve a very important problem that they were grappling with and not really able to find a solution to. So they called a TRIZ team and they did a brainstorming and they came up with an interesting solution which apparently solved the problem. So let me show you. Okay, but look, it's many times, what happens is that you only hear the success stories, but maybe 98 times out of 100 it doesn't work. and nobody tells you that it didn't work. Okay? They'll only tell you about where it works. So, you have to be a bit careful with these success stories. But nonetheless, I thought it was quite instructive. So let us try and see what was the problem that the Boeing company had proposed. The thing was that they wanted to increase the capacity of this plane, the Boeing 737-100. Okay, and so increase the capacity means they probably wanted to add another 100 passengers. So obviously, people said, yeah, that part is easy. I can redo the interiors of the plane, and I can put in more passengers. But more passengers means more luggage. Obviously, the total weight of the plane will naturally go up. So what you'll require is naturally a more powerful engine, right? You cannot have the same engine and with a much higher load. So what they said is that you'll require a more powerful engine, and that of course Boeing knew. But the problem is that they said, okay, if you require a more powerful engine, then of course what is the engine doing? It's burning fuel, right? And fuel means fuel and oxygen have to combine, and that's how you get combustion, and that's how you get energy. So they realized that the air intake has got to be increased, and also the fuel injection casing. All of that needs to be made much bigger. And they said, yeah, okay, we can do that. But what they found is, because the engines are mounted on the wings of these planes you have seen, when I make the engine much bigger, there's a fear that when the plane is going to land, the engine can go and hit the ground. Because I've just increased the air intake area, and the overall volume has increased, and as a result, the clearance from the ground is likely to be lower. So this is what was the issue. So the team reasoned that they would need the engine air intake and the fuel injection casing to be larger. However, this would decrease the clearance distance between the bottom of the engine and the ground. Okay? So the improving feature is engine volume, and engine volume in turn means a more powerful engine, and therefore you can have a plane with a more bigger capacity. All that is fine, but the worsening feature is the length of the moving object, the clearance. From in this particular case is the clearance, and it's a moving object because it's an aeroplane. And so you can see, I mean, both of these, this engine volume, okay, is there. Engine volume, you can see number 7. It's an improving feature, so it's vertically put. Okay, number 7 is engine volume, and the worsening feature is the length of the moving object. Length means clearance. Now, this is another thing that these terms can be applied in very, very different ways. So you will have to see what it means for you. Okay. So length of the moving object, let's say, is the worsening feature. As I said, length means the clearance between the ground and the engine. Okay. And so at the intersection, what they found by looking at the TRIZ template was that these are the numbers which appeared: 1, 7, 4, 35. So we can actually verify this. Like, yeah, you can see 3 and 7, right? 7 is volume of moving object, and 3 is length of the object. So let's say this. Okay, this is the intersection. You can see 1, 7, 4, and 35. Everybody can see that?
Yes, sir.
Yes, sir.
Okay. All right. Yeah. So you can see that it is the same number. I just wanted to check 1, 7, 4, and 35. Okay. So what they said is that these are the ones which it would be best to concentrate on. Now, let us go and look at what were 1, 7, 4, and 35 in terms of the principle. One was segmentation, 4 asymmetry, 7 nested doll, and 35 was parameter changes. Okay, so these are the four. Now, by parameter changes, like for example, suppose you are taking a fuel like kerosene or whatever is used in an aeroplane. But suppose you say that I'm going to take a totally different fuel. You know, I could actually, like you saw, that you could even do a combustion of ammonia, and you can make it react, of course, with air, and it will form nitrogen and water. Of course, I still need the air intake area. That's what parameter change means, when I'm carrying out a totally different approach to try and solve the problem. But that's not what they were interested in. They were interested in 1, 4, and 7. They didn't want those kinds of solutions. They thought it's not practical. So these were the ones: segmentation, okay, asymmetry, and nested doll. Now, what they said is that firstly, you remember how Bosch actually segmented the ammonia converter, right? And put a soft metal lining, inside the main thing, and was able to segment the functions of a reactor. And so he wanted the soft lining to be able to hold the pressure long enough so that the reaction takes place, and then after that the hydrogen is allowed to pass through from that liner, and by the time it attacks the main frame, that it's lost all its pressure, and hydrogen was only very potent and dangerous at the higher pressures. I mean, so that's how they solve the problem, by a segmentation. So what they said is that we have the engine air intake area and the area of the casing surrounding the intake. So that's what they mean. This is, let's say, the air intake area, and this is the casing around the air intake area. And so they said, look at the two differently, the air intake and the casing. Now, then number 4 was asymmetry. Now, this is very interesting. It's a spinning blades which are drawing in air. It has to be obviously covering a circle, right? So they said that the air intake area must be circular. There's no choice, because you have a fan blade which has to spin. Okay? So they said, yes, it has to be circular. But what were they trying to do? They were trying to make it bigger, right? They wanted to make the air intake area bigger. And then what they said is, yeah, okay, the air intake area must be circular, but does the total thing, that is the casing, does that have to be also circular? They said not necessarily. Why should it be circular? That can be something else. And so what they did was that they flattened out the casing at the bottom, and they made the casing asymmetric. But you can see that the air intake area is circular. Okay? And this air intake area is larger than this air intake area. But the way they had mounted this whole thing, it turned out that there was no difference in the in the clearance. So the biggest problem was that the reduced clearance from the ground they were able to take care of. And the other principle, of course, it follows, what do we have? It says components or parts of a system being nested within a supersystem to conserve space. Use unused volume, contain one thing inside another in a controlled way, or have one part pass through the cavity of another part. That is what nested doll is. And so what he said is, all I have to do is ensure that the symmetrical blades are properly nested inside this asymmetric structure. Of course, it was possible to do. And these were really the three principles which they used. And in fact, if you actually observe some of these aeroplane engines next time you're flying, you will actually find that they are not these kinds of completely symmetric shapes. They look like this. Okay, it's flattened at the bottom, and it is basically to create a better clearance. And it was solved by this. Otherwise they probably were not getting the right idea about how exactly to go about cracking the problem. Is it clear to everyone? Did you understand?
Yes, sir. Sir, but doesn't this affect the aerodynamic ability of the plane?
This is a very good point. It can only point you in a direction. Obviously, the engineers will after that have to go and look at that could there be some negative attributes of the suggestion. So I'm sure someone would have gone and done that and found that it doesn't make any difference. But can it not affect the aerodynamics? Right?
Yes, sir.
Maybe it could, but probably at first tested out after the idea was proposed and found to be not significant. Okay?
Yes, sir.
Everybody understood the way the problem was solved?
Yes, sir.
Now, all that is fine, but I kept asking myself that what is the relevance in chemical technology? For example, can you really apply it? And so I thought, let me take this important contradiction, which is that how do you manage the contradiction in an exothermic reaction? Okay? Because after all, we know that great companies like BASF were able to manage the contradiction. And there's no better example of that than the sulfuric acid process, which is, as you know, very strongly exothermic, and at the same time that you cannot have a low conversion, and they achieve something like 99% conversion. So how did BASF manage? Of course, BASF managed it by very innovative thinking. And those are probably the kinds of ideas that Altshuller incorporated. I don't know whether the work of BASF was included or not in his thinking, but let us look at it. Now, I've also seen, and I'll send you, there are a few publications on using it in chemical technology. But what I found is that those people had made their own features, and then they tried to apply the TRIZ methodology. Somehow I did not find that so interesting. I felt that Altshuller has put in a lot of thought, and let us see if using his features, whether we can try and find a solution to this problem of the contradiction in exothermic reactions like the contact process. Okay, so what did we say are the is the contradiction that when you have an exothermic reaction, there is a buildup of heat. Consequently, there's a rise in temperature, and that could speed up the reaction, right? I felt that the improving feature would be the speed. It's a speed of object, but it can be any speed of reaction. Okay, I felt that maybe this could be taken as the improving feature, and the worsening feature was really what? It was the quantity of substance. Maybe these two could be the kinds of features that we should focus on. Does anyone have a view on this? Does it seem sensible? These features, do they look all right?
Yes, sir.
This is the at the heart of it, because if you get that wrong, then you'll be in a wrong box. Then you look for the wrong principles. Okay, but I'll also show you that I looked at it in more than one way. I'll tell you about that also. Okay, so rate of reaction is number 9. Okay, improving feature, and quantity of substance 26 is the worsening feature. So let us go back to number 9. Okay. So 9 is the improving feature, and 26 is the worsening feature. Okay. So there is over here, if you look at that intersection, we're talking about 10, 19, 29, and 38. When I saw what exactly these mean, and I will send you 2 files, one which gives you a little more of a description of these various principles and what they mean, and what all they can mean, and also of the features. You can go through it more carefully. Okay, but 10 was it says preliminary action. Perform before it is needed the required change of an object, either fully or partially. So that is preliminary action. 19 is periodic action. Okay? Periodic action is that when, for example, when we are pushing in a nail into the wall, what do? We don't just use the hammer and just push on the nail. You hammer the nail, which means that periodically you are applying a force. That's what you are doing. This kind of periodic action you'll also find, for example, in these ambulances and all, or in factories. These sirens, they will have some kind of a pulsating sound. That's also periodic action. Or if somebody needs to be given a massage, has a heart attack, and what do? You actually give chest compressions, and you don't just go and sit on the chest, but you give chest compressions, maybe 5 chest compressions, and you're okay. And 29 was pneumatics and hydraulics, and what it says is that use gas and liquid parts of an object instead of a solid part. So it's talking about inflatable things, air cushion, that kind of approaches. Okay, and 38 was strong oxidant. I mean, in some cases, you might be able to solve the problem with the help of a strong oxidant. Now, when I looked at the solution which BASF came up with, okay, and which many of you have studied in your industrial engineering chemistry course, was what did they do? They actually started this is, let's say, the profile of conversion with temperature, and obviously as you go to higher temperatures, the conversion falls. and it's an exothermic reaction, and at the higher temperatures the conversion falls. So whereas you really want to be close to 100% conversion, you know. And so what BASF did was that initially they put it in one catalyst bed, and they just let the exotherm build up. They didn't care about the rise in temperature. Why didn't they worry about the rise in temperature? Because at that point it's still very far from equilibrium. So I don't have to be very concerned about the equilibrium at that point. When I'm more in the initial and middle stages of my reaction, I need to worry about it a lot more as I go into this, and that's what they did. I mean, they were able to achieve, say, 60% conversion very fast because of this rise in temperature. Then what they did was they took out the intermediate stream and they did a heat exchange, right? And they cooled it down, okay, to the original temperature, and again let the thing react adiabatically. So there was a rise in temperature, and again repeated this process. That's how they were able to get the best of both worlds, where they were able to get a very high initial rates of reactions, where you could achieve more or less about 80-90% of the conversion at a fairly fast rate. And it was only in the later beds, that when the temperature dropped, that the rate of reaction would have dropped. And the way they took care of that was by really driving the equilibrium through Le Chatelier's principle by absorbing the SO3 which was formed in sulfuric acid. And so then I could drive the equilibrium further to the right. And also they may have used a catalyst which was a lower temperature catalyst in the final bed. I don't need a low temperature catalyst initially, but I need it over here. And so maybe that would have been another way that they speeded up this whole thing. Another advantage that they had out of this is, when I let the temperature rise adiabatically, I've got a very high quality of heat because it's at a very high temperature. And so when I'm doing the heat exchange, I can generate very high pressure steam. Okay? And that's how they generated power from utilizing that heat. Whereas imagine, suppose I had said, let me carry out the reaction isothermally, keeping the temperature at 400 degrees centigrade, the quality of the heat that is evolved would be low. The overall rate of the reaction would be very low because I am at a very low temperature all the way. Of course, I will get conversion, but I'll have so many other constraints that I may not want to do it. And that's what BASF did. They did not do it in an isothermal mode. Although conversion-wise, you would expect the highest conversion if you left it at the isothermal mode. They came to the end later on, not initially. And exactly the same thing they also replicated in ammonia synthesis, where adiabatically, then they do a heat exchange, again do adiabatically, and that's how they moved up this conversion curve. And here in this particular case, they liquefied the ammonia, and so took out the ammonia as the product, and therefore now I don't have product, and I could drive the equilibrium further to the right with following the Le Chatelier principle. So this is what is really done. Okay? Now, if you have to look at these, do any of these things appear to be in line with what is actually done? Any of these four principles?
Yes, sir. They are like after reaching 60% conversion, then they are cooling the whole product, and then again they are starting.
Yeah.
So that is kind of a periodic action.
Brilliant. Yeah, you can see. See, I just applied it to this. Suppose, like, let's say I was not smart enough as BSF, and surely we aren't, but you may have got some kind of a guidance on how you might try and go about solving the problem. It's not to say that that's the only thing that will help you, but I found it really remarkable that actually what is being done is periodic action. Okay. Is that clear to everyone?
Yes, sir.
Everybody understood? But let me tell you that I was not absolutely comfortable with the selection of the features, and I asked myself, have I been over optimistic in selecting those? Instead of speed of reaction, okay, I can also look at that if I had done the reaction under the isothermal reversible type of condition, that there would be a loss of time, and I don't want that. I want to do it faster. So the improving feature that I might be looking for is loss of time, means that there is less loss of time. I don't want to lose so much time. And the worsening feature is, of course, the quantity of substance. So I said maybe loss of time also is not a bad way to look at the feature rather than the speed. Okay, and I mean, and there is a relationship between the two. I mean, they're not completely sort of mutually exclusive. So when I looked at the loss of time and worsening feature and quantity of substance, loss of time is 25. Okay, and quantity of substance is 26. Quantity of substance. So we can look at the intersection of 25 and 26. So that is 25, and then I go to 26, and that is your 35, 38, 18, 16. That's what I wrote, 35, 38, 18, 16. Now, when I was looking at this one doesn't give me periodic action. It gives another 4. Parameter change, strong oxidants. Some of these things you'll find sometimes are common. Okay, mechanical vibration, partial or excessive action. Now, I just felt that partial or excessive action is a possibility. Now, let me try and explain to you what is meant by partial or excessive action. Okay? Like, for example, if you are filling up your car in a petrol pump, what does that guy do? If you say fill up my tank, that guy will put in that money and insert the nozzle into your tank. And what you find is that initially the petrol is being filled up very fast. Okay, and towards the end, when your tank is starting to get full, what happens is that it slows down just so that it's not spilling over. And so if you look at it, that's not very different from again the periodic action, where you're just letting the first part take place very fast, and only towards the end you're slowing it down, and therefore it looked like that this partial or excessive action is actually a good way of doing it. That's exactly what you're doing. You're just doing it very fast initially and slowing it down. Okay? You're just slowing it down as you're moving more and more towards the 100% conversion. But here, I'm doing it very, very fast. And, parameter change, which was not there in the other one, parameter change could be that where let's say after the reaction has taken place and I'm taking out the SO3 and ammonia, and so I've got a new set of conditions now with the product having been taken out, and so to that extent parameter change is perhaps also indicated. But certainly in terms of the most innovative approach, I think the partial or excessive action seems to be a good approach. In other words, I felt that even if you take not exactly the same features, but of course the features have got to make sense, that you actually can come up with a fairly interesting solution. Is this sulfuric acid thing clear? Any suggestions or alternative thoughts from anyone?
Sir, is there a way to implement the 38 principle, like the strong oxidant thing? Can we incorporate that also?
Yeah, that's very interesting. I mean, you see, you could, especially of course in the case of, obviously not in the case of ammonia synthesis, because that's a reducing reaction. But if I were to look at sulfuric acid, then of course, instead of using oxygen, I could have used something else to oxidize SO2 to SO3. I could have used chlorine. Okay? And then, of course, it would be a completely different method of carrying out the reaction. Obviously, you don't want to necessarily do such drastic changes, because that an industry may not be interested in. Industry may be interested within the certain boundaries, that if I can improve things. Is that clear?
Yes, sir.
Did the methodology make sense to you? Or at least did you understand the approach?
Yes, sir.
Okay, great. There were two more things that TRIZ says. And let me also tell you that there are also some algorithms. I think it's called ARIZ, ARIZE, which is a computer program. So you can actually play with that. And there's another thing called SUF, very, very high-end practitioners of TRIZ. They might use such approaches in trying to solve it. I mean, I didn't want to go into all those complex things. But the other two principles which I found very interesting, one was that wherever practicable, look for solutions from within. It's quite amazing how you can come up with extremely innovative solutions. And I found that in many of our work, we did not call it solution from within, but that's exactly what we did. So I'll take you through a few examples. But before I do that, let me first show you, again, from the contact process, a great thing of solution from within. Okay? Now, what happens is that these are the beds. This is your periodic action that is done, your catalyst beds. And first you take molten sulfur and push in air, and it forms SO2, and then you are putting it through your beds where SO2 is getting converted to SO3. Now, the thing about the contact process, which a lot of people don't realize, that you must use extremely dry air, because if you don't, when the SO3 is being formed, and if there's some moisture, it will form a mist of sulfuric acid. And that can create a whole host of other problems. So you want it to be a strictly gas phase without any mist. So it's very important to make sure that the air which you are using to first convert sulfur to SO2 and then SO2 to SO3 is absolutely dry. Let me ask you, what would be some ways to dry the air?
So by absorbing the moisture using some adsorbents like sodium sulfate also.
Absorbent, isn't it?
Yes.
Absolutely, that's what you would have thought. Or maybe a lot of people like you use anhydrous sodium sulfate or anhydrous calcium chloride, and you can dry it. But that's not what BASF did. You see, sulfuric acid, concentrated sulfuric acid itself is one of the best drying agents. I mean, very few things are as potent as concentrated sulfuric acid. So what they did was the product, the concentrated sulfuric acid, which I produced from the contact process, they actually put it into this initial vessel. Concentrated sulfuric acid is falling down and your air is traveling up. So there's a counter current, okay? And the concentrated sulfuric acid is used to dry the air. So it's a wonderful solution from within. I don't need any other reagent, chemical, nothing from outside. And you know, where people teach about vanadium pentose, all that is fine. But there are so many other cleverness in these processes which really comes out of things like searching from a solution from within. And look at the other beauty of it, that sulfuric acid, when it picks up moisture from air, obviously it gets a bit diluted, and it is that slightly diluted sulfuric acid which is put along with some more water. So you make it maybe about 95% sulfuric acid, and that is what is pumped into these absorbing vessels. And the SO3 which is coming from all of this is finally reacting with this 95 to 97% sulfuric acid and getting converted into oleum. So that's the process. I mean, it's not as if you put SO3 into water. You put it into 95 to 97% sulfuric acid. So even the moisture in the air was taken advantage of. So it's a really superb process and clearly a solution from within. Is it clear to everyone? Everybody understood?
Yes, sir.
Okay. Let me take you through, as I said, I always ask myself, did we do something which followed some of these principles in our work? Even if I didn't know the name, later on always I can say, yes, this was that. Around 2003, we are tied up with Mercedes-Benz, the Daimler corporation in Germany. It was probably one of the most visionary projects that India has ever done, okay? Where our aim was to make oil from wastelands, you know, and Mercedes were very, very interested in the work, you know. And previous to that, we had actually made small amounts, maybe a few liters of biodiesel from the Genrikh plant. You know, if you have heard of Genrikh biodiesel, let me tell you, it is this work which actually made it so famous globally. So what happened was that you know, they looked at our biodiesel and they said, hey, it's not bad, but it required some areas of improvement, okay? And we were able to improve it, okay? And finally, you know, they felt that we had been able to make a very good quality biodiesel. I myself was shocked. They sent, I see this article, Merck to run on pure biodiesel. Now, let me tell you what is the significance. This was the first time ever in the world that neat biodiesel, not that it's a blend of some biodiesel with fossil diesel, neat 100% biodiesel was actually being tried out, you know. And it's visionary companies like Mercedes that can do it. You don't expect everybody to be able to take such initiative. And we were extremely fortunate that they had tied up with us, you know. But what happened was that it was one thing to prepare in the laboratory a few liters of biodiesel of a super quality, okay? But when I realized what they wanted, they had plans of running two of their C-class Mercedes, one to the northern part of India and one to the southern part of India with our biodiesel. And they said that they will require about 2,000 liters of biodiesel for these trials. And I said, 2,000 liters? How are we going to make this? And we did not have a clue. It's very easy to make biodiesel. Okay, it's very easy. It's just a trans-esterification reaction. So you take let's say an oil, okay, and you take a catalyst and methanol, and you're doing a trans-esterification and being left with a methyl ester. There's nothing so difficult about it, and you get glycerol as a side product. The problem is that many times this reaction is not 100% complete. So you might end up with maybe some diglyceride or monoglyceride, where all of these have not completely reacted and formed this. Some of it could be still in the diglyceride or monoglyceride form. It could be that some of the solvent and the catalyst that you have taken could end up in your fuel that will completely corrode the engine, and some of your glycerol also could remain. And if you have got even traces of moisture while this reaction is taking place, you see you have got the perfect recipe for a saponification. You have got catalyst, which is something like sodium hydroxide or potassium hydroxide, and then you have got water, you've got an oil. So it can form a soap, and there is oil, it can form a thick emulsion. And that's exactly what was happening. So when we were doing it in the laboratory, we had to take care of those problems. And I said, there's no way breaking down the emulsion, etc. was a horrendously complicated task. I said, 2,000 liters we are going to produce like this, and we had barely a month or month and a half to go. I realized this is not going to work. What is very, very interesting is that what was clear to me is that, you see, what was being normally done is that once I do the reaction to remove this, let's say potassium hydroxide, methanol, etc., we were adding water. And so with the expectation that the water will take out all this, glycerol is soluble in water, whereas your biodiesel is not soluble in water. So all the impurities will go down, and I'll be only left with the biodiesel. But the problem was, as I told you, because of the saponification which can take place, especially if your reaction is not completed, okay, that you will end up with soap. And so that's exactly what was happening. So I said there has to be a different way of cleaning up the biodiesel without adding water. Means I have to take out all these impurities. Taking out the methanol was simple. I mean, you can just apply a vacuum, and you can pull out all the methanol. I used to look at this reaction. In fact, people would think I'm mad. Look at the reaction and see what's happening. What was clear to me was that if we could add more glycerol from the outside, that glycerol is excellent at sucking out all the impurities from the biodiesel, and everything else will go into the glycerol, and I'll be left with more or less a pure biodiesel. So why wasn't it happening during the reaction? Well, because the amount of glycerol which was being formed was not sufficient. So what we did is, glycerol was a byproduct. So we again, we purified the glycerol, recovered some pure glycerol from our byproduct, and added more glycerol from the outside. Outside means from this process, okay, just so that all of these impurities can be taken out completely. Okay? Once those impurities had gone, you could give a final wash with water when there is absolutely no impurity, but just in case, just to be on the safe side, we would give a wash with water, and there's absolutely no emulsion formation. And that is the biodiesel which made our institute famous in the world. And what did we do? We actually found a solution from within. What was that solution? I said, I'm not going to add anything from outside, and I'm not going to add any water. What was I left with? The only choice was really the glycerol. When we observed the ability of glycerol to mop up these impurities, that was it. So that was, it was just amazing. It was tested out all over the world. Okay, there was a study which was done in the EU where they evaluated the best biodiesels from which anybody could provide. Again, there it came out number one. You know, and in fact, I remember still that when we sent this biodiesel for this kind of an international testing opposite the whatever was the best in the world, this person was the head of that institute in Austria. He wrote, impressively good. Did you distill the jet for biodiesel? That's what he thought we did. He said, otherwise, it's not possible to make such a pure biodiesel. I remember he told me, Dr. Guru, nobody has made it. He didn't know what we did. We just found a solution from within. And that's what got patented the world over. Okay. Is that clear? Did all of you understand?
Yes, sir.
Okay. Now let me take you through another solution from within. Okay. Now, what happened was, I of course told you, and our institute was very big in salt. And the little run of Kutch is one place where they produce something like, or at least at that time, they were producing about 5 million tons of salt. And it is produced by very poor people, migratory workers. They come around sometime around September, after the rains, and they stick around there till about June before the monsoon. And then once the rain starts, they again go back. So for about that 8 months, they are, they make the great little run of Kutch their home. Some of them come with their families, their husband, wife, kids. They all come and they stay there. And what are they doing? They're producing salt. Now, in the little run of Kutch, the salt is not produced from seawater. There's no seawater in the little run of Kutch. What they do is that the underground brine, which I told you, the subsoil brine, is very saline. It's about 4 times the salinity of seawater. And that was the attraction, that it is so efficient to produce salt. 4 times the, imagine how much your evaporation load comes down, because it's 4 times the concentration. Okay. So what they do is that they use this DG sets and they pump out, water from the underground, and then these are all the pans. So they charge the water into that pan, the brine actually, and then it evaporates, and the normal way in which salt is produced is produced. Now, what happened was that the little run of Kutch, if you have ever been there, it's like a desert. There's for miles together, there's nothing there. And as I told you, the underground water is saline. And it is such a vast stretch of land. There's not a drop of water to drink. And, people would initially be bringing it through tankers. But then I got a call from the industries commissioner in Gujarat, and he because he knew about the work on membrane, and he thought that maybe we can put a reverse osmosis plant there. So he called me and he said, Dr. Ghosh, these people don't have any water to drink. Can you put up an RO and give them some water? I said, RO, it will never work, because it's 4 times the salinity, the water, the underground water. It is no way you can do desalination. The osmotic pressure would be very high. You simply cannot do it. So it will have to be some other solution. Then he told me, do whatever you want. Take as much money as you want, but give me a solution. And my colleagues, okay, there was a person called Dr. S.T. Rajan. He had tried out some solutions based on solar still, etc. But somehow nothing looked very practical. When we went to do it, it wasn't good enough. And it was a sudden thing. I said, look, there is brine, of course. There's water. It's just that it's not a drinkable water. But there's water. And they are using this DG set to pump out brine from the underground So, the flue gases are coming out hot. The temperature at which they come out, outlet, immediately at the outlet will be something like 300, 400 degrees centigrade. I said, look, why can't we use this waste heat to desalinate the brine? Is it possible to do? And I had some brilliant mechanical engineers, Dr. Desley is now in NCL Pune, and there was another person, Dr. Pothal, who came to us from NIT in Rourkela, mechanical engineers. And I said, look, Dr. Desley, can you make some kind of a heat exchanger which will allow us to heat up the brine using the flue gas? And second is, look, this is to be done in a way that these are all the poorest people. Don't make a sophisticated device. It should be something, because there's so much of salt, in the brine. So there will be always salt encrustation, and so it will have to be a system that is easy to clean up. And so they said, "Don't worry, we have understood what you want." And these brilliant guys then went and made this heat exchanger here. And the other thing was very nicely done with copper tubing, and where the flue gases are going to the inside of the tube, and so there's no back pressure or anything generated from this unit. The hot gases just pass through, but they heat up the brine, and we could make absolutely pure water at something like maybe about 1 to 2 liters per hour. But these things operate round the clock, 24 hours. They're keeping on pumping brine. So there's no problem. You could use this unit, and a family could get maybe about 20 liters from a unit. Okay. And so when the Industries Commissioner said, make me 200 of these. And that's what all the people were using, 200 of these units to give them water. What did we do at the end of it? We just found a solution from within, okay? Because nothing else was practical. We had brine and we had waste heat. We didn't require anything else. So I hope you have got another example of utilization of or finding a solution from within. Everything that I'm telling you was novel enough that all of these were granted US patents. So look for solutions from within. Any questions? All clear?
Yes, sir.
Yes, sir. Can you explain how fresh water was generated by using heat exchanger again? I just missed
Yeah. So what we have is, you see, this is your heat exchanger. So there are tubes, copper tubes, and the hot gas, the flue gas from this unit, from the engine, is passing through that copper tube. And on the outside, you have the brine, which is falling on those tubes. So the brine gets heated up to beyond 100 degrees centigrade, and it basically generates steam. Then we were just condensing that steam and getting the water. Is that clear?
Yes, yes.
That's the distillation process. Now, let me show you another example of a solution from within. You can see that this patent has been granted to ICT just last year, and the international patent has also been cleared. Now, it's a problem, and by the way, I mean, this has got many dimensions, this particular approach. Now, what happens is that in coastal areas, like for example, you go to the coast of Gujarat, and all the major producers of soda ash, chloralkali, okay, they're all located along the coast. Okay? Why are they located along the coast? Because their raw material is basically sodium chloride. It is sodium chloride which is being converted into soda ash by the Solvay process, or electrolysis, and you convert it into caustic soda and chlorine, by the chloralkali process, as you know. That's the reason why all of the soda ash plants are set up there. But the problem is that which you might have learnt about when you were taking your courses. You see, that salt has to be dissolved in very pure water for the to practice the solve process. You cannot, for example, dissolve salt in seawater and then use that for the soda ash manufacture. Why is that? Because you use ammonia in the process, as you know. Okay, ammonia is getting recycled, but ammonia is used, and that ammonia can react with all the impurities in your seawater like magnesium and calcium, etc. Okay, and it will form things like magnesium hydroxide. So you cannot do that. You need very pure water to dissolve your salt. How is the pure water normally obtained? Many of these guys have large RO plants, very large. Okay? And so what they do is they do seawater desalination. Okay, they generate fresh water, and then they add the sodium chloride to it, and that is your saturated brine, which you get, and then you let's say put it for your solve process, or it could be the chloralkali process. Now, this was always troubling me because, as you know, that reverse osmosis takes a fair amount of energy. It's a non-spontaneous process. Osmotic pressure of seawater is 26 bar, and typically these RO plants, you have to apply something like 70 bar pressure. So you can imagine that it's a high pressure process requiring not only a high capital cost, but also very high energy requirement. Believe it or not, it was an idea which was generated in our canteen, ICT canteen. I mean, I was eating lunch with some people and we were discussing something, and I don't know what happened, and suddenly this idea came to my mind. So what happened was that what I said is, look, I mean, this is what they need. They need saturated brine. Okay? Now, you look at saturated brine, it's got an osmotic pressure of something like around 300 bar. Is the osmotic pressure of saturated sodium chloride. And the osmotic pressure of seawater is around 25, 26 bar. So we were working in the area of forward osmosis, which is the conventional osmosis, where you have a membrane, and as you know, water will flow from the region of low osmotic pressure to the region of high osmotic pressure. That's osmosis. That's what Van 't Hoff did and developed his osmosis equation, the Van 't Hoff equation, phi is equal to CRT. What we are doing is that we are not doing RO, we are passing seawater through this module from, these are hollow fibers, so from the inside tubes, we pass the seawater, and from the outside, the shell side, we pass this saturated brine. The water from the seawater, and only mind you, the pure water, there's no salt that permeates across the membrane, only pure water permeates. It's sucked in because of the very high osmotic pressure of the saturated brine. So at the outlet now, suppose let's say I pushed 1 liter of saturated brine, let's say per minute through this module. At the outlet, it would draw in so much of the pure water from the seawater that 1 liter might become 2.5 liters. But it is no longer saturated. Why? Because it had pulled in water from the thing. So I cannot, it's not a sustainable process. But here was a very, very simple idea that we had. Why don't we resaturate the outlet brine with more NaCl? After all, NaCl is my feedstock. That is what the solvay plants, etc. use. So I'm just adding NaCl into this, resaturating. So I make the resaturated brine. Now, if I started with 1 liter or 1 kg, I might have finally ended up with 3 kg. I recycle my 1 kg in my process so that I have a continuous process, and 2 kg now goes as saturated brine for production of soda ash or for production of chloralkali. In terms of the flux, in terms of anything you name it, it's comparable to RO. If anything, it gives you a much higher productivity. And because it is a spontaneous process, osmosis is a spontaneous process, the only energy that I need to incur is the circulation cost. I just need to circulate these things through this module. That's it, under ambient pressure. There's no 70 bar pressure, there's nothing. Okay? So we completely bypassed this approach of first generating fresh water and then dissolving the salt to make the saturated brine. Instead, we just prepare a saturated brine. The water permeates directly into the saturated brine, creates undersaturated brine. We add more NaCl, dissolve, which is a simple operation. And you can now have a continuously self-sustaining process. Is that clear to everyone? Did everybody understand?
Sir, I have a doubt here. Since we are returning the concentrated seawater back into the sea, yes. So after a considerable amount of time that this process has been taken out, doesn't the concentration of the seawater will also increase from what it is now?
Very good point. You see, the people who are doing seawater RO, they are also producing concentrated brine.
Yes.
Okay.
Yes.
And in fact, they produce concentrated brine, which is twice the concentration of seawater because their recovery is about 45 to 50%. If you try to make your recovery very low, usually you'll pay a higher penalty from the overall energy requirement. In our case, because it's a spontaneous process, I don't need to push out 50% water. And in fact, what you can see over here is that our percentage recovery over here is 33%. We can make it still lower. If required, we can just make it 25% so that the seawater salinity only increases by 25%. You got it?
Yes. Yes, sir.
Okay. But, and second, the best is that if your soda ash plant is backward integrated with salt manufacture, then use this concentrated seawater to produce salt. Don't throw it back into the sea. And the productivity of your salt will be higher because naturally the concentrated seawater will give you a higher productivity of salt production. Is that clear?
Yes, yes.
So that is the most ideal solution. But if they are not backward integrated, you can discharge it into the sea, okay? And with something like a 25% increase in the salinity, what you can also do is that you can draw in some seawater, dilute the concentrate prior to discharge. Okay?
Yes, sir. Yes. Thank you.
There is another thing which TRIZ says, which is extremely interesting. What it says is that use defect as resource. Let us try and understand what is defect. And you may have already seen, if not all of you, some of you probably would have seen this particular illustration, which I will show you now, and of what is meant by the most ideal solution. What this is, have any of you seen this figure before? Anyone? Of soap being filled into soap boxes. Has anyone seen this?
No,
I suppose
really.
no one, right?
No, sir.
Okay, good. That makes it even better. Okay. Now, so it is talking about a very interesting problem. What it is saying is that you can imagine when you go to a factory which is producing soap, okay, and there are thousands and thousands of soap cakes, being packed into boxes every hour. So you have very high speed lines. These are empty boxes. Okay, these are your empty boxes. This is your soap falling into the box. Okay, And can you imagine what a perfect alignment is required, for the soap to fall into the empty box? And then once it falls into the box, it goes, okay, over here, and you just put on the lid, and that's it. That's being sold in the market. But every so often, what happens is that an empty box misses the soap. So it comes out and it is not got any soap in it. It's not surprising because it's such a high speed operation. So obviously you cannot shift or you cannot sell empty boxes of soap. So you need to make sure that those empty boxes of soap are removed before packing into the cartons and selling the filled boxes of soap. What would be the best solution, or what would you do?
So maybe later on in the line, we can have a sensor that detects empty soap boxes. Maybe depending on the weight of the soap boxes filled. So filled soap boxes will have a certain weight requirement, and anything below that is sort of like knocked out by the sensor. Something on that sort.
Right. But you
Sir,
can imagine the speed with which these boxes are moving. Any measurement always requires a certain finite amount of time. And so it will have to accurately, or not, if not accurately, it will have to make the measurement very fast. So there is a problem. And then, okay, so I make the measurement. And then after that, what will you do? You'll just remove those boxes, right?
Yes, sir.
I have a better option.
Yeah.
Sir, we can forward in the further in the line, we can put a air jet kind of thing that will blow some air. So if the box would be empty, it will fly out, and if it will be filled one, then it won't fly
Oh
out.
my God, you're a genius. That's wonderful. That is the solution which was proposed. Okay. And so what you have is, just like you said, you have a strong draft of wind. So you could have fans, and so boxes will topple over. What have we done? We have used the defect itself as the solution. You understand? We did not have a second solution, and you have detected and solved the problem both at one go. It's not that you did first a weighing and then you remove the boxes. The wind is strong enough only to blow away the empty boxes. So it does both actions together. In other words, you use the defect, which is the empty box, light box, as the solution. Is that clear to everyone?
Yes, sir.
You can have many solutions. You'll have to see whether you can come up with the most brilliant solution. I used to find this user defect, and this is very popular. But I said, could there be some others where we actually have done something similar? And just try to recollect when we talked about the lithium-ion battery, and I told you about the work that Yoshino did, where he put in a separator, which was a porous polyethylene film over here, separating the anode and cathode compartments. What he was trying to do was that in case there is any unexpected heating up, heat buildup, some short circuiting, something that happens that heats up the lithium-ion battery, what will happen is that the heat fuses all the pores, and now it becomes like a impermeable film, okay? And so it cuts off the anode compartment from the cathode compartment, and it becomes like an internal fuse, okay? So what did I do? I used the defect, the heat, and the consequent rise in temperature as my solution to the problem. And that, by the way, is also the principle of operating any fuse. And you take a low melting an alloy, which cuts off the circuit. So it's not as uncommon as we think it is. You can look at this kind of an approach in so many areas. I was just trying to see, for example, an aeroplane. Obviously, if the aeroplane is overweight, there are too many passengers or too much luggage, it's unsafe to fly. Of course, today, the moment the pilots detect it, they will offload some of the luggage or offload some of the passengers. But if there was a way of being able to automatically measure the weight of the plane just before takeoff, and then if that sensor can give that feedback to the engine, you know, that the engine will not start if your plane is overweight. So, in other words, I'm using the problem itself as the solution.